Welcome to the ultimate test of a senior engineer, designing a system that can handle the sheer volume of a global newsfeed. We begin at the edge. A user types a quick status update on their phone and hits publish. That simple action sends a payload across the network, seeking a home in our data centers. Looking at this high-level routing diagram, the request hits a load balancer, distributing traffic to web servers. These act as traffic cops, directing the payload to the post service. Its primary job is persistence, writing the update into a database and a cache. Up to this point, the logic seems bulletproof. The data is safely stored. It is tempting to assume that building the feed for a user's friends is just a matter of querying this database on demand, sorting by timestamp, and returning the results. This documentation shows how that assumption treats the entire operation as a basic HTTP post request, passing a simple text payload and an authorization token to authenticate the user. For a prototype with a few thousand users, this linear design works perfectly, but scale changes the physics of the system. Asking a database to perform complex relational joins across millions of users every time someone refreshes their app guarantees an immediate and catastrophic system failure. The primary threat to any distributed social system is the hotspot key problem, often called the celebrity problem. Data is sharded across multiple servers to handle load, but if everyone tries to read data from a massive celebrity at the exact same moment, all that traffic funnels into a single database shard, overwhelming it with read operations, while the rest of the cluster sits idle. When a global icon with 100 million followers drops a new photo, the system cannot afford to calculate who needs to see that post at the exact moment those followers open their app. To survive this volume, the architecture shifts to a pre-computed read model. We move the heavy computational lifting away from the read request, pushing it entirely to the exact moment the original post is written. The system evolves from a passive database waiting to be queried into an active distribution engine. It relies on a principle called write amplification. Let's trace how this distribution engine actually processes a post, starting back at the perimeter with the web servers. As outlined in this architecture block, before any payload reaches the internal data pipeline, the web servers execute two strict operational guards: authentication and rate limiting. The system limits the number of posts a single account can make within a specific time window. This acts as a vital buffer, blocking automated spam and abusive content from flooding the downstream processing queues. Once the payload passes these checks, the web server hands the post off to the Fanout service, and the asynchronous delivery process begins. Isolating security protocols and traffic shaping in the stateless web tier protects the fragile internal network, ensuring the asynchronous pipeline only processes verified, valid data. Fanout is the exact mechanism of delivering a newly published post to the individual feeds of every single person on a user's friend list. Looking at the Fanout architecture, the service first queries a specialized graph database to retrieve a complete list of friend IDs. It filters out muted accounts, packages the final list of recipients alongside the new post ID, and drops them into a message queue. A fleet of dedicated Fanout workers continuously pulls these tasks from the queue, executing the final step of the write amplification process. These workers update the news feed cache, which is structured as a highly optimized mapping table linking a specific post ID to a target user ID. Storing complete post data, like text strings and images, for every user would instantly exhaust server memory. By storing only the IDs, the system maintains a strict configurable memory limit while keeping cache miss rates incredibly low. The newsfeed cache does not function as a traditional database. It is a prioritized list of pointers, trading data completeness for extreme retrieval speed. This documentation compares two diametrically opposed delivery models: Fanout on write, known as the push model, and Fanout on read, or the pull model. For the vast majority of users, the push model is the optimal choice. Because the feed is pre-computed during the initial write, the end user gets immediate, real-time performance the second they open their app. The pull model takes the opposite approach. It waits until a user explicitly requests their feed before generating it. This entirely avoids the hotkey problem, saving massive amounts of computing power for accounts that rarely log in. A scalable architecture relies on a hybrid strategy. The system pushes data for 99% of the user base, but forces the millions of followers of a celebrity to pull the content on demand. Even with a hybrid model, heavy traffic can still cluster unevenly. Implementing consistent hashing ensures that requests and data are distributed smoothly across the available server pool, preventing isolated overloads. There is no single perfect architecture. The system scales by dynamically switching its delivery models, on the fly, reacting directly to the density of the social graph. When a user decides to check their timeline, the client application issues a GET request to the newsfeed service. This sequence diagram maps the retrieval path. The newsfeed service hits the cache and pulls the list of relevant post IDs. But IDs alone are useless to a human reader. The service must now consult several independent caches to construct the actual interface. This process is called hydration. The system takes that raw list of post IDs and fetches the associated usernames, profile pictures, and text content to build a fully structured JSON response. Heavy media payloads, like images and videos, are intentionally excluded from this data packet. The client pulls those directly from a content delivery network, keeping the core API response lightweight and fast. The cache architecture supporting this hydration is split into 5 distinct layers: newsfeed IDs, post content, social graph relationships, user actions like replies, and numeric counters for likes and follows. Sub-second latency is achieved by decomposing what feels like a single feed into dozens of parallel network requests across these specialized high-speed memory layers. As systems expand to handle video files and richer content, decoupling components becomes mandatory. This diagram shows how message queues act as buffers between the download, encoding, and upload modules. If a cluster of servers gets bogged down compressing a heavy 4K video file, the message queue simply holds the incoming tasks. The bottleneck is isolated, and the rest of the publishing pipeline continues to operate without stalling. To ensure that heavy media doesn't compromise system security, clients use pre-signed URLs, granting temporary restricted access to upload files directly to the storage buckets. Coping with the celebrity problem and the massive load of a global user base inevitably forces databases to be heavily denormalized. Clean relational data structures are sacrificed to ensure queries execute entirely within a single table. System design rarely provides a single correct answer. Building a product at this scale requires a deep understanding of the brutal trade-offs between read latency, write amplification, and the pure operational complexity of keeping the servers online.